All right, in sections 3 and 4, as we said, we are going to look at reading and writing chemical equations. So by now you've seen plenty of examples of chemical equations, and you know that this is how we represent a chemical reaction. We want to break down what we're seeing in the reaction. So when we see something that looks like A plus B yields C plus D, we have things on the left of the arrow and things on the right of the arrow. Anything that's on the left-hand side of the arrow is what we're going to call our reactants. And then anything that's on the right-hand side of the arrow are what we're going to define as products, the things being produced. So these are the things that are reacting. These are the things that are being produced. Now, something else you'll very often see, and that you should start getting used to putting into your chemical equations, is the state of each reactant or product in parentheses. So that's where you see things like solid or liquid or gas, or even this AQ for aqueous, just means it's dissolved in water, it's in aqueous solution. All right, so here they are as you see them in your book. A little bit easier to read than my chicken scratch with the pen on here. So you do want to note where table 7.1 is in the book and just get used to these abbreviations. You just put them as shown right here in parentheses after each particular chemical species that you have. And this explains to you that besides the gas, liquid, and solid, you have this aqueous state, which just indicates that a substance is dissolved in water in particular. Now, when a substance is dissolved in water, we call that a solution, and that's what we will be looking at in section 7.5. Okay, and it also leads to plenty of bad chemistry puns, like if it's not part of the precipitate, it's part of the solution, or chemists have all the solutions, or technically alcohol is a solution. So you'll get plenty of bad puns on that one. All right, so now let's just look at an example of a chemical equation and kind of break down what we're talking about. And the one we're going to use is the combustion of methane gas. Now, methane gas is natural gas. It is CH4, as shown here. And in combustion, what's going to happen is that gas, whatever the fuel is going to combine with oxygen as O2. And if a combustion is carried out to completion, the only two products you'll get are carbon dioxide and water vapor as a gas. So we're going to represent the reaction with the equation that we see right here. We have CH4, okay, one molecule of that, plus an O2 molecule. Okay, these are our two reactants. My pen does not want to work today. And then we say they react to yield. Okay, so yields or produces CO2 plus H2O. Those are our products. Now, if we include the states in that, the equation that we see looks like this one down here. So we note that CH4 is a gas. We note that O2 is a gas, CO2, and H2O. Everything in here is going to be in the gaseous state. So we want to include that so that somebody realizes we're not talking about liquid water or dry ice or something like that. All right, so now if we look at it and break it down, we know that matter cannot be created or destroyed. So that means that whatever we started with in terms of atoms, we need to end with those same atoms. Now, that doesn't mean that the compound or the molecule can't be broken apart, but it's not going to be destroyed. It's just going to be rearranged. It's like breaking apart our Lego bricks and putting them together in a different way. So if we look at our equation and we say, how many oxygen atoms do we have on each side of the equation? Well, starting out the way I had it written, I had just the O2 over here, so I've got 2 oxygen atoms on the reactant side, and then I produced a CO2, so I had 2 oxygen atoms in my product here, and then H2O, I have an oxygen atom over here. So I started with 2 oxygen atoms, and I ended with 3 oxygen atoms the way I have it written. That cannot be. What happened? We cannot create matter. We can't destroy matter. So what's going on? Well, the thing is, we have to account for the atoms on both sides of the equation. It just means that in my chemical equation, I'm not showing the whole story. I can't have just one molecule of oxygen react and form both carbon dioxide and water. I've got to have more oxygen atoms. And what I have to do is keep it going until I get everybody balanced out. Okay, now the other thing, notice if we look at the other elements. Okay, if we look at hydrogen atoms, notice on the left side of the equation, we have 4 hydrogen atoms in that methane, and over here we made a water molecule. We only have 2. You know, again, what happened? We can't have that. We can't have 4 on the left and 2 on the right. It looks like 2 hydrogen atoms have been destroyed. We've lost them, and we know they haven't been destroyed. So what we have to do to correct that misimpression is create what we call a balanced equation. We have to balance the number of atoms on both sides of that arrow. Okay, so everything over here has to match everything over here, in terms of numbers at least. Now, to balance the equation, we have to be careful about how we do it. We are going to insert coefficients, which are numbers that come before the atom or molecule, not subscripts. Remember, the subscripts are telling us the number of each type of atom within a molecule. If we change the subscript, we are changing the very basic chemical nature of that compound. And we don't want to do that. We're not changing the compound. We just want to change the number of them that we have. Okay, so that's what we indicate with the coefficient. So notice here, we started with 1 methane. Okay, that's supposed to be a 1. And I'm just going to go to doing it that way. And then we have 2 oxygens. Okay. If we double up that oxygen to 2, now we have a total of, here we have 1 carbon, and we have 4 hydrogen. Now over here, by doubling that up to 2, we now have 4 oxygen atoms. Okay, that's supposed to be oxygen, not 40. Here, we're going to keep 1 carbon dioxide molecule, so that gives us 1 carbon. And we've got 2 oxygens here, and then we're going to double up to 2 of the water molecules. So now over here we have 4 hydrogens, and we have 2 oxygens, and if we add these 2 oxygens to these 2 oxygens, we see that we have 4 oxygens. So now we've got 1 carbon and 1 carbon. Okay, so that's good. We have 4 hydrogens and 4 hydrogens, so those are good. And we have a total of 4 oxygens and 4 oxygens. We are good to go on the oxygens. The equation is now balanced because the number of each type of atom on both sides of the equation have become equal. So nothing got created, nothing got destroyed, it just got rearranged. We were able to take the Lego blocks over here on the left, break them apart, and rearrange them to make the new Lego buildings over on the right. That's all we're doing. We're popping them apart, putting them together a different way. Now, once we have tried balancing an equation, we want to double check it, or if we're working on balancing the equation, we kind of need a little checklist. We need a way to check ourselves and make sure we have enough. So the number of any particular type of atom within a chemical formula that is embedded within an equation is, we get that number by multiplying the subscript and the coefficient, okay? So multiply, subscript, and coefficient. Okay, if you don't see a coefficient or a subscript, that is an implied 1, so you can just put a 1 in. And then you go through and you look for coefficients, so there's a 1, a 2, a 1, and a 2, and you multiply that through by the subscripts, so an understood 1 for carbon right here, and then 4 hydrogens, 2 oxygens, understood 1 for carbon, 2 oxygens, 2 hydrogens, and an understood 1 for the oxygen here. Okay, so I can go through and I can make a running total. I can say on my reactant side, how many carbons, how many hydrogens, how many oxygens. Product side, do the same thing, have a running tally, and then make sure it's the same on both. If it's not, then I need to start working my way through and multiplying some of those in order to get it to where I want it to be. So the numbers of each type of atoms on both sides of the equation are equal, and we have a balanced equation. Okay, that is what we need to show that combustion reaction as a balanced equation. So how are we going to write our balanced chemical equations? The first thing you're going to do is write what we call a skeletal equation that just has the correct chemical formulas for each of the reactants and products. So this is where it's critical to look back on the skills that we've been building up in all the other chapters. Okay, Chapter 5 has your nomenclature rules. So that will tell you how to go from the name of a compound to the formula of a compound, how to make sure that you have the right subscripts in there to balance charges out, that you have a neutral compound. Where are you starting from? Okay, those correct chemical formulas are critical to writing a balanced equation. That's the first thing you have to do. Make sure you have the right compounds. Now, if an element occurs in only one compound on both sides of the equation, start with that one. That's where you start. So, in other words, if I have sodium chloride on one side and sodium hydroxide on the other side, but then for the sodium chloride I started with, I have chlorine gas and something else with chloride in it on the other side. It's in 2 places. I don't want to start with the chloride. I don't want to start with something that is split up throughout the equation. So only on one place on the left, only on one place on the right. Start with that. If there's more than one, start with the metals. Balance your metals before the nonmetals. Keeping it in order will help you to do it more smoothly, more quickly. Now the other thing, if an element occurs as what we call a free element, so not a compound. If it is by itself, and if it's a diatomic, that's okay. So if you have things like, if you just have magnesium metal as a solid, or you have oxygen gas, anything like that, if it is just an element, even if it's a diatomic or something to that effect, balance that last. That's your ace in the hole. You're going to keep that one to help balance out everything else. And you can balance free elements by adjusting the coefficient just on the free element. So in other words, if you have, for instance, H2, plus, where's my eraser here? I'm sure it goes away when I'm looking for it. Let's get that eraser. Let's take that one out. Okay, let's go back to our pen here. Now, if I have H2 plus O2 yields H2O, I've got oxygen as a free element right here on the reactant side, and it's combined with H2O on this side. If I were to need to balance the oxygen, I would start by adjusting the coefficient over here. I would not want to adjust the coefficient on the H2O first, because when I do that, I'm affecting the hydrogen as well as the oxygen. But over here, I'm only affecting the oxygen. So I can use this one to balance that one out more quickly. Now, number 4, if the balanced equation contains coefficient fractions. Now, what do we mean by coefficient fractions? Well, over here, let's say we're balancing this one. I had H2 and I have O2 yields H2O, and I have 2 hydrogens on the left, 2 hydrogens on the right. I have 2 oxygens on the left and only 1 oxygen on the right. Now, I don't want to do anything to H2O because then it messes with my hydrogen and I have to do something else. So what I could do, H2 plus O2 yields H2O. Now, again, by inspection, this is a simple one. They're not all as simple as this. You could say, well, if I changed H2O, then I could change hydrogen over here, and that would balance out quickly. Yeah, but theoretically, the easiest way for me to balance my H2O is if I can, over here I have only one oxygen. Okay, I want to turn this into 1. I have 2, I want 1. So if I cut it in half, or I multiply by a half, then 1/2 of 2 oxygens is only 1 oxygen. Now I've got 1 oxygen theoretically on both sides. But we don't want these fractions, okay? So if we have, in this case, the coefficient fraction of 1/2, I change them into whole numbers by multiplying the entire equation by whatever I need to get rid of the fraction. So for instance, for 1/2, I need to multiply by 2, so 2 times 1/2 is equal to 1. If I do that, I can't do it just to the fraction. I have to do that to everything in here. So I'm going to multiply that by 2, I'm going to multiply 2 by 1/2, and I'm going to put a 2 here. So what I end up with then is 2H2, see if I have room to write it in down here, 2H2 plus, now it's just 2 times 1/2 is just a single O2, yields 2H2O. Okay, so I have to be careful to make sure that I am keeping whole number coefficients all the way through. It's okay to use a fraction just to get something to balance, but then be sure you go back and get that fraction out of there before you call it a balanced equation. Once you've done all this, you need to check to make sure your equation is balanced, okay, by summing the total number of each type of atom on both sides of the equation. Make sure that the total of carbons on the left equals carbons on the right, hydrogen on the left equals hydrogen on the right, so on and so forth. Biggest thing to remember right here, change only the coefficients to balance the equation. Never change the subscripts. Never, 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 never. Okay? That is a big no-no. Changing the subscripts changes the nature of the compound. Can't do that. So running through an example, we're going to use what we learned in Chapter 5 and what we just talked about here to write skeletal equations for reactants and products, and then we will go through and balance. So we're starting here with the reaction of solid aluminum. So we would write that as Al solid with aqueous sulfuric acid. Now the aqueous tips us off that it's going to be the AQ. Sulfuric acid, we learned naming that compound in Chapter 5. That was going to be the oxo acid for sulfate, so it's H2SO4. And then it is aqueous. That is going to form aqueous aluminum sulfate. So here's our formula for aluminum sulfate, and we're told it's aqueous, so we put an AQ. And then hydrogen gas. Hydrogen is a polyatomic, H2, and then we have to indicate that it is a gas. Now, before we can do anything else, we have to be absolutely sure that we have the correct formulas for these. So aluminum in its atomic state is just aluminum. Okay, sulfuric acid, make sure we have 2 of those hydrogens to balance out the 2- charge on the sulfate, H2SO4. Here we know that aluminum is a 3+ ion. That's one of those indeterminate charges. It's fixed charge. Sulfate, SO4, is a 2-, so we had to have 2 of the aluminums, 2 times the 3+ to get 6+, 3 of the sulfates times the 2- to get 6- so that it balances out. So we know that formula is good. And then it's remembering that hydrogen gas is one of those diatomic molecules. All right, so there's our skeletal equation that we're going to start with. And we start examining this. What are we going to do with this thing to balance it out? Well, now the first thing we're going to do is look for those pure elements. Anything we have that exists by itself. And we have 2 of them. We have aluminum and hydrogen, aluminum in the reactant side and hydrogen in the product side. Okay, so we're going to save those for last. We don't want to touch those yet. Okay, so we're not messing with the aluminum here, we're not messing with the hydrogen, so that leaves us these two things to start with. Now, let's look at what we have in there. If we look at sulfuric acid, we've got hydrogen, sulfur, and oxygen in that one. And if we look, hydrogen occurs in only one place on the left, only one place on the right, but we've got that pure element, so we don't want to touch that yet. Sulfur and oxygen both appear only here and only here, so we're going to start with those. We're going to start with sulfur and oxygen. Now, the thing is, when we're looking at this, sulfur and oxygen are part of a polyatomic ion, and it didn't change from one side to the other. Sometimes a polyatomic ion gets broken apart, but in this case it didn't. It remained as sulfate on the left, sulfate on the right. So when that happens, that makes life a lot easier. We can balance polyatomic ions as a unit. We can imagine now that what we have on both sides, we have aluminum, we have hydrogen, and we have sulfate. We're going to leave it as just SO4. All right, and we said we were going to start with the sulfur and oxygen as a sulfate unit. If we look, we started out, and ignore the red 3 that is in the skeletal equation right now. Let's look at what we started with. We started with 1 aluminum. We started with 2 hydrogens, again ignoring the 3 that's there, and we started with 1 sulfate. Okay, that was on the reactant side. Now, if we look on the product side, over here, we had 2 aluminums, we had 3 sulfates, and we have 2 hydrogens. All right, and we're starting with the sulfate. We have 3 on the right in the products, 1 on the left, so that's where the 3 comes from. Right, when we do that, now that changes everything that's in the sulfate molecule right here. The 3 times the 2 in the hydrogen brings us up to 3 times 2 is 6. So we now have 6 hydrogens on the left and 3 sulfates. Okay, so now sulfate is balanced. That one's good. And we still are looking at the hydrogen and the aluminum. Okay, so let's see what we do next with those. All right, so let's get our running total going here. We had aluminum, and we have hydrogen, and we have sulfate, and we are currently up to 1, again ignoring the red number, 1 of those, 6 of these, 3 of these, and then on the product side we have 2 aluminums, we have 3 sulfates, and we have 2 hydrogens. All right, so we took care of our sulfate, that's good. Now we can look at the 2 we said to leave for last, and we'll just start with the aluminum. We have 2 on the left or the right, and we have 1 on the left, so we put in a 2. That affects nothing but the aluminum, so now aluminum is balanced. That leaves just the hydrogen. Okay, so we have 6 on the left, 2 on the right. All right, since this is already a 2, we've got to increase it to 6, but we don't want to put a 6 out in front because remember it multiplies through. So we put a 3 here. 3 times 2 gives us the 6. So now we have 2 aluminum, 6 hydrogen, and 3 sulfate on each side of that equation. That gives us a balanced equation. All right, so here they're just summing to make sure the number of atoms on both sides is balanced. They've made a checklist, and they did this one just as atoms. So aluminum, 2 on both sides. Hydrogen, 6 on both sides. Now they're breaking the sulfate apart. They're multiplying through. 3 sulfur, 12 oxygen on each side. But you can just balance it as sulfate, because again, in this case, the sulfate never broke apart. It just broke away from whatever cation it was with. Okay, either way, that works. Now, balancing equations is one of those things that some equations are very simple to balance. You can do them just by looking at them, easy inspection. Some of them are a little bit trickier. They're harder to do, and there are some various tips and tricks that you can use to make it easier. If you get stuck balancing equations, let me know. Give me a call, send me an email. I can show you some tricks and some shortcuts. To try to show you all of those would be impractical here because there are so many different types of equations, and there are little things that you may not see on a frequent basis. But if you get stuck on one, again, you can do it just by trial and error, but don't spend too much time trying to balance just one equation. If you get stuck, give me a call. Let me know. We'll work through that one. All right, so that is the basics of reading and writing and balancing chemical equations. Now in the next section, we're going to start looking at how to bring those together in different types of reactions, and eventually what we're going to work toward is writing a more realistic view of these aqueous equations known as net ionic equations. Okay.